things. We can't work with prions. If I told them I was working with mad cow disease in here, they'd shut down the whole block. We can't work with viruses because viruses have to have host cells to kill. Specialized, we need a carbon dioxide incubator, we need to use blood serum to throw the cells in. So we can't work with viruses. We work with bacteria in our lab. We talk about those other things, and that's why we say this class should be called bacteriology and a few other small things. And then we also talk about the body's response, immunology, and how to kill or control these microbes, which would be sterilization, disinfection, and antibiotics. And antivirals. So anyway, when bacteriology became a science in the early 1900s, and the father of microbiology is Louis Pasteur, the man who did the most on bacterial than anything. I mean, Louis Pasteur is amazing. If you look up in the Bible of microbiology called Bergey's Manual, you'll find about 2/3 of the microbes were first described and seen by Louis Pasteur. And this is just absolutely amazing. By the way, he didn't get a Nobel Prize. Why? The Nobel Prize hadn't been invented then. When he was an old man, all of his discoveries were old stuff when the Nobel Prize came into being. But, you know, he is the one that came up with so many things like hand washing. He's the one that proved the germ theory of contamination and disease, that microbes smaller than the eye is what caused contamination and disease. He did so many things. He made the very first vaccine. Well, actually the very second vaccine, rabies vaccine. It's just amazing what Louis Pasteur did. But anyway, when bacteriology came into being, they said we need a standard microbe, a standard measurement, and a standard microbe. Now there's one bacteria that we know the most about. I used to say we know everything about it, but you know that's a big mistake in science. You never say you know everything about something because someone will discover something new. But we know nearly everything about this microbe. We know all of its genes. We know that it's helpful to us. We know it lives on us. It gives us all kinds of benefits. We know that 1 or 2 strains of it that are toxic and can kill us because of the way we raise beef. Yes, and the name of the microbe is Escherichia coli or E. coli. And all of you have it in you, and most of you have it on your hands right now. And it is perfectly harmless in 236 of the 238 strains of it. And the 2 strains that are dangerous do come from the way we raise cows for meat, in which we feed them back their own poop to get efficiency. But anyway, so Escherichia coli became the standard organism because we know it and study it and all of this. And so they measured it, and it's 10 to the minus 6th, or a millionth of a meter long, by 0.5 times 10 to the 6th, or a half of a million wide. And so somebody said, okay, if it's 10 to the minus 6 long and half that wide, we need a standard measurement for what 1 times 10 to the minus 6 is. And someone said, so we need to name it. Someone else said, well, it has to sound small. And so someone else said, well, why don't we call it, it came from a microbe, so why don't we call it a micron? And so the standard measurement of bacteriology became the standard measurement of the standard organism, E. coli. And so 1 times 10 to the minus 6 is the standard measurement in bacteriology, and it is a micron, and it is a made-up word, and E. coli is 1 times 10 to the 6 long by half of that wide. It is a taco bacillus. It's not cocci, and it's not a bacillus. We call it a coccobacillus, but remember, anything that's not perfectly round is a rod. So it is considered a rod, even though it's almost as round as it is long. And the abbreviation was mu. Now, nobody knows where that is on their computer, so we usually just type it U. Okay? So the abbreviation for this was mu. And it was wonderful. I learned it in college, and in my master's, and in my PhD, and everybody was happy. And then we had a fad. You know fads. Educational fads and scientific fads pass through us. What's the color this year? There's a color that's the fad this year. Anybody know? Orange is the new black. Yes, burnt orange is the color this year. Next year will be something else. Last year it was black. So the new black is orange. All right, so when there are fads in science, things change. And this fad was actually a very good fad. Came through, and it is. The more we know about science, the more we're giving names to things, the more we can't remember them all. And all of these parts of the human body and everything else that we're naming, we better stop naming them by people. I mean, really, think about it. Yeah, you know it's considered tacky and low class to try to name a microbe after yourself anymore. If I discovered a new bacteria, I couldn't call it Hixane or something like that. That's considered low class and tacky. You are supposed to name things by where they come from or what they look like. And so this is the fad that went through microbiology, to get rid of things that are named after people and to get rid of things that are named just randomly. For instance, Cowper's gland. On the male reproductive system, there is this gland discovered by Dr. Cowper's that gives the slippery to semen. And they called it the Cowper's gland. And this structure in women that carries the egg, Dr. Fallopian discovered it, so they call it fallopian tube. And so all of this is just a nightmare, because if they keep naming things after people, no one's going to know what everything is. And so they said, okay, let's get rid of Cowper's gland. Let's name it by what its shape is and where it's located. So it's called bulbal urethral gland now. And the fallopian tube is called oviduct. It carries ova, and it's a tube. Oviduct. Wow. And so then they got to microbiology. And they said, what does micron mean? And we said, nothing. It just sounds small, and it sounds scientific. And they said, well, it's got to go. And then so they said, well, micrometer means a millionth of a meter, and isn't it a millionth of a meter? And we said, yeah. And they said, okay, so the micron is going to be called the micrometer. And since the old abbreviation was mu, and since we want to make it metric, we're just going to call it mu-m. And that's the new abbreviation or the standard unit in bacteriology. Now, you will never hear me call it a micrometer. I can't help it. 10 years of university, I called it a micron. I will still call it a micron. Just remember, it's a micrometer. All right, so that was our first measurement in microbiology. The standard unit, micrometer now, used to be the micron. Remember, I still don't know where that whole mu is on my computer. And that's great. And if you see a biologist or a bacteriologist, they will always use microns or micrometers. But people come to microbiology from other sciences. Mathematicians and engineers come to microbiology. And when they get there, they like to use what they're comfortable measuring things with. And physicists and engineers and mathematicians are much more logical than us. they're not thinking about E. coli. They're thinking about the physics of life. And so which do human beings like to work with? Do you like to work with fractions and decimals, or do you prefer whole numbers? Whole numbers. And so the wavelength of white light, which you have to use to visualize anything, is 550 nanometers, or 0.55 micrometers. So physicists and mathematicians and people that come from the math side of science to microbiology measure things in nanometers. That's 10 to the minus 9. Now biologists and microbiologists and bacteriologists hate that. Do you know your 9? 9 to 12, 9 to 14. So, if you see a diagram and it's in nanometers, who wrote it? A mathematician, a physicist, or an engineer. If you see something in microbiology that is measuring bacteria and it's in micrometers, it's from a biologist or a bacteriologist. Now what about the virologist? Remember, 10,000 times smaller than bacteria are viruses. Viruses are itty-bitty things. And you've got to look at them. Well, guess what? There is a number, a measuring system that virologists love. Remember, they were all brought up under the metric system, base 10. And they love angstroms. An angstrom is 1 times 10 to the minus 10. What's the advantage of using that as a measurement? To multiply and divide, all you have to do is add and subtract exponents. So the angstrom is good for something really, really small. And virologists love it. But there are 2 major problems. One, it's named after a person named Angstrom. 2, where is that on your computer? A capital A with a 0 above it. Where in the world is that abbreviation? Nobody knows. So, here's the second big problem with it. You may need to hold on to something. I don't want you to fall out of your chair. 40% of all advanced microbiology, virology, textbooks, journals, and specialized publications are bought by people who are not scientists. 40% of the virology journals are bought by people on the street that are just curious. There are people that will walk through Borders bookstore and pick up a microbiology text and pay $150 to read it that are not taking microbiology. You don't even read it, and you paid for it. Now, everything in the world revolves around one little thing, and what's it called? Money. And these publishers want to make more money, and they don't want to drive off the customers that bring in 40% of their profit. So I want you to do this. This is my little fun exercise. Close your eyes. Do it! Close your eyes. I want you to visualize a chihuahua. Got it? Okay. I want you to visualize a Saint Bernard. Got it? Okay. Now, a Volkswagen Beetle. Okay? Good. Now we're going to do the big one. I'm going to give you a number and I want you to visualize it. 0.000000001 meter. You can't do it, can you? Nobody can. If you tell someone that it's a millionth of a meter, people get an idea of what a millionth of a meter is. They know what a meter is and they know what a millionth is. But 10 to the minus 10 meter, no one has a clue except a virologist. So, the publishers went to the heads of the journals and the societies that regulate all of microbiology and virology and all of those sciences, and they got them to pass a resolution banning the use of the angstrom for these two reasons. One, nobody knows how big it is and can visualize it. The average person can. And two, it violates the rule of we're not using names anymore. So, remember, angstroms are forbidden. They're verboten. Now, when a virologist publishes a paper with their new virus, guess what they do? They put the measurements of the virus in angstrom, submit it to the publisher. The publisher takes whites it out, and changes it to nanometers. Sends it back to the virologist, who whites it out and puts it back in angstroms. And it is published in nanometers, but in parentheses, they put angstroms. Even though angstroms are forbidden. Absolutely forbidden. Okay, so now we're going to talk about energy, and you're going to remember that to visualize something, you've got to bounce wavelengths of light that we can see off of it. The shorter the wavelengths, the greater the detail. Why? The short wavelengths go between two lines. What is detail? Everybody think about this. What is detail? You know, if you go outside, you're going to see. What is that? Isn't that what it looks like? Handicap thing? Something like that? Yeah? Okay? Not much detail there. And you call an artist in, and you'll have a modern artist, and you'll say, paint an apple and a banana, and they'll go, and you get a classical artist, and they'll be going, what are they doing? They're adding lines. And you get better and better, the lines get closer and closer together. All right, so to see detail, that means that the lines are closer together. When lines are closer together, to see that, you have to have wavelengths of light that are short enough to pass between them and bounce back to your eye. So, remember, to see the greatest detail of visible light, you have to use the shortest shade of light we can see. All these colors together is white light. And by the way, who made this? Who made this diagram? A biologist or an engineer? Biologist. It's in micrometers. We don't care about decimals. Screw them. This would be 550 nanometers if it was an engineer. So remember that when you want to visualize the greatest detail of the smallest item, you're going to use this color of light, and that's the filter that's on our microscope. You're not going to use red, which is what I like to look under. I look back, or hot apple pie at McDonald's, infrared. Okay. Now, we can't see these, but we can use these in microscopes, and we'll talk about that a little bit later. All right, so we're at this point, and let's see what else I'm going to do. This is resolution, which I was just talking about. If the light you're shining can pass between them, you see them as two. If it can't, you see it as one fuzzy. And we're going to start there next time. So what am I going to do now? I'm going to take out our microscope and go over a few things with you. And you don't ask any more dang... Oh, I got to do one thing. I forgot one thing. I forgot to show you where the other practice questions are. So as this is, as soon as this shuts down, I'll bring it back up. it's coming back up, I'm going to show you some things about your microscope and how we clean it, how we store it, and how we focus it. And then we will go and cry. All right, so here's how you have to store it. And this is what the checkers will be checking each time. And so let me just kind of show you how to store it. It should be clicked on the shortest objective, which is 4x. So the objectives that we use in this class here are the objectives on yours. 4x is called scanning, and we use it for storage. 10x is called load, and we use it for focusing. 40x is called high dry, and we do not use it at all. All we do is clean it because it gets gooey. That's for using for paramecium and for those sorts of things, fungi and so forth. And then the one we use 99% of the time is called oil immersion or oil. So we use this one and we use that one, and this one's for storage. All right. You're going to click the 4x into place, and we're going to go over the parts of the microscope right now. This is the foot. Duh. Okay. And right here, this little wheel is the power wheel, and it clicks. Listen. Roll it toward you. Pull it back towards you and click it off. When you take it out, you've got to make sure it's off. If you plug it in while it's on, it blows the bulb, and that's $50. So you want to make sure it's off when you pull it out. Everything between the foot and the stage where you put your slide is called the stage. It's called the condenser apparatus. And the condenser apparatus is made up of the light source, which is the bulb. And usually the bulb is one of the blue or purple ones. If it's not have a blue or purple bulb on it, then it has a filter that is purple or blue. The iris diaphragm that opens and closes and shrinks or widens a beam just like the iris in your eye. And the condenser lens, which is the first magnifying glass that concentrates the beam. So everything under here is called, between the foot and the stage, is the condenser apparatus. Light source, filter if needed. If the bulb is not purple or blue, there's a filter. Then the condenser lens, and then what opens and closes it is the iris diaphragm. What you put the stage on is called, what you put the slide on is called the stage. And from above, the stage, why don't you do that? From down, if you're looking down, the stage looks like this, with a hole in it that the condenser comes up into and is even. You lay your slide across this hole, and the back of the slide and the condenser should almost touch. Now in in a real hospital lab, you would put a drop of oil on that condenser and it would touch the back of the slide, and that way light would not pass through air when it left the light source. But we don't do that because you're students, and that's the most disgusting form of life on earth. Students are Americans here, and they believe more is better. And if so they can't focus, they'll put another drop, and another drop, and another drop. And then soon we'll have oil pouring off the condenser into the light source. You will smell it burning, and you can fry bacon. And it's a mess to clean up, so I don't even tell students they can do that. You can't do it. Don't do it. All right, then the slide is held in a cutout called a slide holder that has a pincher here that holds it. So you need to pull this little pincher open and push the slide up completely inside this cutout. If you put it here, it will, when you let the pincher go, it will eventually shoot it across the room. So you want to make sure it's in the cutout. Then, hanging down off the left side of the microscope, there are two circles. And what that does is move this backwards and forwards and up and down. And this is called the stage adjustment. So this is the stage adjustment. One moves it forward and backwards, one right and left. Okay, on the other side, black knob, is the condenser height knob. So you can bring the condenser up to almost touch the back of the slide and bring as much light as possible through the slide. What else did I want to tell you about it? Okay, this is called the nose piece, and our microscope, you can change the objectives, each one having a different power, by turning the nose piece ring. Do not grab the lens or the objective to change it. Why? Before World War II, all objectives hung off the nose piece the same distance. So you had this nose piece, and they all hung off the same distance. As a result, each one had to be focused independently. The higher the power, the less focal plane you have to work with. So when you get to 100, you have less than 1 centimeter that you can move it to make it in focus. And as a result, you cannot use the coarse adjustment. There is no way you can move it small enough amount to bring it into focus. It took hours to focus a microscope. But some smart engineer figured out that each lens, if you hang it off the nose piece so that the right distance for focus, where this one's in focus, and you hang that one a distance so that it's in focus, when you get this one in focus and swing this one into place, it will be in focus also. And this is called parafocal. So after World War II, all microscopes began to be designed so they are parafocal, where the objectives are hung off the nose piece in such a manner that when one is in focus, they all are. And you think, well, what's the big deal? Think about that. The longer the objective, the more magnification. Now, if you look at the ends of these, this one has a huge place for light to enter, and this one's smaller. And when you get down to the oil, it has a pinprick of a hole. And the distance that you have to focus them is only that much on that one, this much on this one, and this much to focus on that one. If they're all focused when one's focused, you have this much to work with if you do with this one. Now look how much you have to work with to go to this one. So we focus with this one. Once this is in focus, we switch this one into place and then fine tune, and it's perfect. Why do you care? Because if you put your slide here and you put it too much, you drive the lens through the slide, break the slide, and scratch the lens. If you put the slide here on a 10X, there is no way you can bring it down low enough to hit the slide. So the advantage of being parafocal is you can focus, you have a longer focal plane to work with on 10X, and there's no way you can break the lens or the microscope or the slide. Once you get it perfectly focused that way, you swing the oil objective into place, and it will click right into where it's supposed to be, and all you have to do is fine tune. So, that's the advantage of this. Now, the eyepiece up here is called the ocular, and it's 10X. and then you have the 4x, the 10x, the 40x, and the 100x. And so, if you're using this one, and you have this one clicked in place, you've done 40 magnification. If you have this one and this one, it's 100, and it's 400, and then this one is 1,000. And microbes are 1,000 times smaller than the human eye can see, so that's why we use this one. Now, before World War II, these were 12x in Japan and Germany. Now, why do we care? Because of this. The best human eyes can see is 0.42 micron detail. That's okay. We can't see any shorter wavelength than that. We get that. That makes good sense to us. But another thing is that the more magnifying glass there is, the longer the tube. But the longer the tube, the smaller the hole. Now, what if the hole is smaller than the wavelength of light you're trying to force into it? That is the physical limitation of your microscope. If we put blue light that is 0.42 microns wavelength, the distance between this is 0.42, but the hole is 0.40. What were you going to see? Nothing. So, at 120, that hole gets too small. So that's why we have 100. X is the longest one we have. Times 12 would give you 1,200. That's the maximum we can get in magnification, because you can't get visible light through that hole. So after World War II, they just changed this to a 10, and there's not much difference between 1,000 and 1,200. At 1,250, you wouldn't see anything. So anyway, the standard is now 10x for the ocular, and the oil immersion lens is 120. You can buy a 120x oil immersion lens, and you will be able to use it, and you can see it with a very short length purple bulb, but it will be very shadowy, very low light conditions. Let's see what else I want to tell you about it. Every microscope has one horrible fault. Did we cover that? Okay. All microscopes have one horrible fault, and that is that those that use oil, and that's everything above 70x uses oil, and we need to talk about why we use oil. Okay, so here you have a slide sitting on a stage with a condenser. And here you have a microscope objective. When light travels through air, it is bent slightly. And so it will pass through air twice, one right here and one there. So that means what you're going to look like looks like that. Do you want to see something like that even though it's a straight line? You don't. It doesn't matter at 10x or at 40. But above 75, that gives you a visible waviness. So what we do is we add a drop of immersion oil that bends light the same amount as the glass in the light source, the glass in the condenser, the glass in the slide, and the glass that makes up the objective all have the same bending power. so that this is a straight line because this oil also does as well. So when you buy a microscope, you buy a microscope with Class A glass lenses. Then you go and buy slides that are Class A. And then you go buy immersion oil that is Class A. And the reason it's type A, because they all have the same bending power. So you get a straight line. So when the light passes through them, it's a straight line instead of passing through oil and then air and then back. So you don't get this zigzaggy appearance. And so that's why there are two reasons for having oil. One, when light leaves a light source, it moves in all directions. Oil concentrates so that all light passing through the drop of oil is concentrated into a beam. Second reason we have oil is because the bending power of this, it's very soft. Clean oil off, push it all the way in, lock the cabinet, and never ever turn this knob. This knob will cause the whole nose piece to turn around and fall off. And a lot of people think they want to be some sort of movie star. That's only on television, not here. So you want to leave that tight, put it in there, and then this is the Staph aureus bug. It's MRSA, multiply resistant Staph aureus bug, and we keep the microscope key on there and we stick it in this drawer. Okay, so that's what I'm going to cover on the microscope. The only thing now I'm going to cover is I'm going to tell you where to find more questions for your practice test, and then we're going to get home. So you'll be home by, you'll be walking out the door by 9. Oh, guess I gotta put my password in. She looked at my password, I saw it. Probably one of those people at the ATM too. Yeah.
So how do you use these to clean the lenses?
Yes.
Objectives?
Yes, and you press up in the objective, and you use a little fingernail to get in there to get the oil off. And then it turns the paper clear when there's oil, and then it does it when it's not.